Let's resume our discussion on complex numbers. We are about to talk about division or fraction of complex numbers and express it as x plus yi form. In this case, the key is to multiply the conjugate of the denominator to both numerator and denominator. What is the conjugate of denominator 2 minus I? It is 2 plus I. So multiply that to both numerator and denominator, and let's see what happens here. Let me increase the font a little bit so you can see these fractions a little bit better. I hope this is better. 2 plus I over 2 plus I, so that's multiplied. So we multiplied it to both numerator and denominator. And denominator, this is what we are going to get because this is a minus b times a plus b form. So this is actually 2 squared minus and then I squared. That's what we get. And then the numerator is simple. It is basically foiling. And as a matter of fact, here I think I skipped a step 2. There's 4i times I. So that should be plus 4i squared. Now whenever I squared show up, we have to change it to negative. Well, that's the rule. That's the general rule. Looks like this is too big. I cannot squeeze in anything anymore here. So let me copy this one down. Okay. This I squared is replaced by negative 1. And then this I squared is replaced by negative 1. Consequently, we have this negative 4. And let's see. Negative of negative, what do we get? We have 2 squared plus 1. And that's typical as a matter of fact. If you do this many times, you'll see the same result all the time. You're going to get, if denominator is a plus bi form, you're going to get a squared plus b squared all the time without exception. That's because if you have a plus b times a minus b, then you're supposed to get a squared minus b squared. But you have a plus bi times a minus bi, so a squared minus b squared I squared. So we have a squared plus b squared. Well, if you didn't really follow what I just said verbally, well, just take a seat and then do several more exercises. 1 more fraction, 2 more fractions, and then 2 more fractions. So it looks like if you go through all these exercises, you'll have to realize the denominators of 1, 2, 3, 4, 5 more fractions. And by doing all those, by multiplying the conjugate of the denominator to both numerator and denominator 5 times and doing those, this kind of process will become very, you're going to get used to this kind of process, and the denominator will look very simple. We're going to get a squared plus b squared, or modulus squared. And simplify further, and we have something like this, and in the end, we have to have x plus yi form, or a plus bi form in the end. You have to. It's a little bit tedious to prove, but it is possible to prove that set of complex numbers is closed under addition, multiplication, subtraction, and also division. Modulus, well, just after calculating z, all you have to do is a squared plus b squared, and it takes square roots there, and it turns out something like this. And then conjugate, just change the sign. Let's do this once more. Let's take problem E. Okay, let's do that. Looks like you'll have to multiply the conjugate of the denominator twice here because there are 2 fractions. And oh my, I decided not to bother with that. Okay, so let's do this one. Do I have solution for this one? No, I didn't. I just left those two students even here. Now that's okay. We have plenty of problems with the answer key. So let's go over this one. Denominator is 1 plus 2i, so multiply 1 minus 2i to both numerator and denominator. And what do we get? We have 1 squared minus 2 squared, and I squared is what I'm gonna get here. So a squared minus b squared form. A plus b times a minus b is a squared minus b squared form. And then finally, negative 3 times negative 2, that's positive 6, and then I squared. Excuse me, I squared, and that's what you get. And then please note that I squared is always negative 1, which means this whole thing will become minus 6. And this will become negative 1, so the whole thing will become plus 2 squared. So we have 5 in denominator, and after simplification, we have negative 1 minus 13i. Detail is left to the students. And then after getting those, you have to add with 1 minus 3i. After some simplification, we get something like this. So we can plot it. 4/5, comma, negative 28 over 5. You can plot it in any graphic paper. If you want complex conjugate, here it is. Change the sign. If you want modulus, a little bit tedious, but here it is. A squared plus b squared, and then, well, we have to do that inside square root. That's about it as for computation of complex numbers are concerned. Addition, too straightforward. Subtraction, just equally as easy. Multiplication requires foiling, so it's a little bit more challenging, but that's still not too bad. Division is important, and you can expect some divisions in the exam, because if you can do division, that means you can do everything. Okay, excuse me. Let's move on to some equations problems this time. If you have a quadratic equation, then you can use quadratic formula to get it done, and that process is purely algebraic. You can complete the square and then manipulate it. So we have something like this, except that this b squared minus 4ac, excuse me. This time, a, b, and c can all be complex numbers. So looks like you'll have to be a little bit careful about all kind of things. Okay, let's go ahead and do that. Say the first problem, how about that? First problem is rather exceptional. It can be easily factored, but oh yeah, I cheated. Instead of going through this quadratic formula, I cheated because this constant term I is 1 times I, and then we have 1 plus I show up over there, so I can actually factor it. And consequently, we have solution z equals -1 or z equals -I. But if you want to do that with this quadratic formula, well, let's try that. So -b, so b in this case is 1 plus I, so let's put 1 plus I there, and then this should be 1 plus I squared minus 4a. A is 1, isn't it? There's nothing there, so 1. And then c is I, so this whole thing becomes 4i. And then 2a, a is 1, so we have something like that. And then, is it possible to simplify it? Well, it should. It should simplify itself. And let's go ahead and do that. Let's see. How much time do we have? Can we do this on time? This can be a bit tedious. Okay, after breaking up parentheses, this is what you get. And then let's break up this parenthesis. We have, let's increase the font so that everybody can see this better. Let's use complete square formula. 1 plus 2i plus I squared. That's the same as 1 plus I squared using the complete square formula. And then let's see, that whole thing is the same as, and this minus 4i and then this 2i cancel out. We have minus 2i. And oh, I see, here is a critical step. We have a complete square again inside the square root. 1 minus I squared and this is what we get. Square and square root cancel out, and we have plus or minus of that. So I don't have to worry too much about absolute value kind of thing. As a matter of fact, this is not real, so absolute value do not matter as a matter of fact. Square and square root cancel out, and we always have plus or minus. And consequently, what we have, z is equal to, when this thing is positive, what do I get? Minus 1 minus I plus 1 minus I, everything divided by 2. So what do you get? 1 and negative 1 cancel out. Minus 2i divided by 2. Yes, after simplification, I get negative I. That's when we have plus sign over here. And we have to consider what happens when we have negative sign. So let's get all this, and then let's consider negative. So this thing is now negative, so this is going to be minus 1, and then I have to change the sign here as well, plus I. Now, do you see cancellation? Negative I and positive I are cancelling out, and negative 1 minus negative 1 over 2, so negative 2 over 2, hey, that's negative 1. And we have two solutions, negative I or negative 1, and the same thing as we expected. I mean, I had this kind of simple solution, factorization and a solution, but the reason I went through all this quadratic formula ordeal is because I just wanted to show you how to work with quadratic formulas in complex number system. This is going to be relatively typical. Excuse me. In order to get this I outside square root, it is always possible, but it's going to be usually difficult. So you'll have to expect some kind of complete square one way or the other. Otherwise, there is some other method called De Moivre's theorem, but that's something we'll have to discuss way later, maybe week 15 or week 14 or something like that. There are other problems, but you can do something similar. I think this problem can be factored as well, but if you do not factor it, then you can use quadratic formula and then do it brute force. If you do factor, I didn't use factorization, I use quadratic formula here, and obviously it could not have been factored, so I could take it back. This probably cannot be factored at all because we have the square root of 3. In any case, here's the situation. Let's see. In this case, inside of the square root becomes just real. So I didn't have to deal with this complete square. But in any case, we're doing this within complex number system. There are a couple more problems that are algebraically a bit more challenging, but I'm going to leave those to students here. this is gonna be a challenging homework set.